Alright, 22. Explain how to compute the work done on a rotating object when you know both the sum of the torques, right? The sum of the torques caused by external forces exerted on the object and the number of rotations. Number of rotations the object makes in the time interval of interest. Well, we know that work is given by this sum of torque external times delta theta. Okay, remember it's similar in the translational analogy. You've got sum of the forces times what? Delta x, right? That's the work done on an object. Okay, so it's similarly with rotation. We have this equation here. Now the thing is, remember, all you've got is the number of rotations. What you need to do in order to get delta theta is you need to multiply the number of rotations by 2 pi to get it to theta. So if you've got one rotation, so if it started there and it went around once, then that's one rotation times 2 pi, and that gives you this delta theta. Or if you've got half a rotation, then you multiply that by 2 pi. Or 17.4 rotations multiplied by 2 pi. Then you can convert it into there. So make sure that you understand that. Okay. 23. If an object's motion is both translational and rotational, how should its kinetic energy be determined? And that is how you determine the kinetic energy. Equation 1233. You've got the kinetic energy of the center of mass plus the rotational kinetic energy. So this is half mv squared, but that is the velocity of the center of mass. And then this is your rotational kinetic energy, half I omega squared. 24. For an object that rolls without slipping, describe what effect static friction has on the work done on the object and on the object's energy. Okay, well, I suggest you go and make sure you understand example 12.8. You've got this ball rolling down this incline, and this is the free body diagram just as for a particle, if you consider that to just be a particle, and this is your extended free body diagram. And you can see here is the friction force. Okay, so you're going to draw your friction is opposing the relative motion of the surfaces. Okay, so there's your friction force in your free body diagram, and there's the friction force in the extended free body diagram. And so here's a nice paragraph. The force of static friction does no work on a rolling object. So you need to make sure you go and check out example 12.8 to go and see why it does no work. Okay? The only thing it does is take away some of the translational kinetic energy, okay, and generate an equal amount of rotational kinetic energy. It takes away translational kinetic energy by reducing the magnitude of the vector sum of the forces and converts it to rotational kinetic energy, causing a torque. So this is on page 322, if I'm not mistaken. And this example is on the previous page. Okay? So make sure you understand why this is the case.